Hey guys, if you are in trig, this is from 7.7 for trig. This is our last lesson of the year. And for pre-cal, this is from 6.7. This is called the dot product. Okay, we are still working with vectors though. So the dot product is an operation that you can do to two vectors. It looks like multiplication, but be careful because it is not. If I give you two separate vectors and I ask you to complete the dot product, you're going to take the two numbers in front of the i's and multiply them, the two numbers in front of the j's and multiply them, and then of course following PEMDAS, once we've multiplied those two numbers, we're just going to add them together. Here your answer is always going to be a number. Okay? So let's look at some examples. Find the dot product of vector v and w. Okay? So I'm going to take my two numbers in front of my i's and I'm going to say v dot w equals 5 times negative 3, okay, plus now my two numbers in front of my j. Make sure to take those signs with you, okay? So then I should have negative 2 times 4. All right, so here we get a negative 15. And then here we get a negative 8. So if I'm adding a negative 8, it's the same as subtracting 8. And then our answer is negative 23. Okay? I'd suggest you try and pause the video and try these two on your own. So the first one says v dot w. Same as what we did on the last question. So here I'm going to take the two numbers in front of the i's and I'm going to say 4 times negative 2 plus the two numbers in front of the j, negative 2 times 3. Okay? And now I end up here with negative 8 and here with a negative 6, which gives me negative 14. Okay, and let's do the second one, v dot v. So pretend like you had written this vector v twice. Okay, I'm going to take the two numbers in front of the I, which when I'm doing the dot product to itself, it has the same number. So if I would have written v twice, the number in front of the first I would have been 4, and the second one would have also been 4. Okay. And then the two numbers in front of the j, if I would have written this twice, would have both been negative 2. And then I end up with 16 plus 4, which gives me 20. And that is dot product. So dot product in and of itself doesn't do much for us. Dot product is used in the formulas that I'm going to be showing you now, okay? So one way we use a dot product is when we want to find the angle between two vectors. So let's say two vectors are drawn in standard position. If I want to be able to find the angle between these two vectors, here's a formula I'm going to use. So I want you to take a quick moment and envision one of these factories. I bet you guys can imagine nowadays factories are much more machine-based than people-based. The machine grabs the product and moves it around. And if the machine has two different arms, you want to know how high up to lift that arm. You need to program with the computers a specific angle for how high you want that arm to lift the product and move it to its next location, if that makes sense, okay? So here I'm looking for a theta. My answer is going to be a degree. And the way I find theta is I do the inverse cosine of the dot product in the numerator. And then in the denominator, remember these two absolute value bars mean magnitude. I have to find the magnitude of v, the magnitude of w, and multiply them together. If you have your calculators, this is, once you write it all out, this can be done in one nice, easy step, okay? So let's start this question off. Find the angle between vectors v and w, okay? Theta is equal to inverse cosine. And then in my numerator, I'm going to put my dot product. So my dot product is my two numbers in front of my i's So I'm going to do 3 times -1 plus my two numbers in front of my j's, -2 times 4. Okay, so this right here is my numerator. It's the dot product over, now I'm going to take a moment and do the magnitude of v. So the magnitude, remember, is square root of a squared plus b squared times the magnitude of w. So I take -1 squared plus 4 squared. All right, so as long as you fill this all out, remember, dot product in the top, multiply the I numbers, multiply the J numbers, add them, and then each of the magnitudes, you can plug all of this in at once into your calculator, okay? So let's take a moment and look at the calculator. It says inverse cosine, and then I literally, with parentheses and negatives, the exact same way, I plugged it into my calculator, okay? If you're just a little off with those parentheses, it could mess you up, so be very careful. I'm a big fan of parentheses. All right. Also, make sure you are in degree mode. If you're in radian mode, I think it gives you like 2 point something. You'll be off. A big mistake that my students make as well is in their radical, they forget to use the right arrow to scoot out of that first radical to then say times the second radical. All right. So be very careful with that. But my answer is 137.7 degrees. Okay. So theta equals 137.7 degrees. All right, let's check out another one just like that. I encourage you to pause and try it on your own. So this one says, find the angle between vector v and vector w. Okay, so theta is equal to inverse cosine of, I have my dot product, so I have the two numbers in front of the i's, 2 times -3, plus my two numbers in front of my j, -2 times 5, over the magnitude of v, square root of a squared plus b squared, don't forget those parentheses, times the square root, now I'm going to do the magnitude of w, -3 squared plus 5 squared. All right. And then from here, just go ahead and take a moment and plug that into your calculator. All right, so if you put that in your calculator, it should look something like this. Let me refocus. All right, so again, remember inverse cosine, you do it by pressing second and then cosine, okay? If you like how I put this fraction, the way I do that is I press alpha, which is my green button, and then I press y equals, and it shows up n over d, which stands for numerator over denominator, and it'll put that fraction bar so that it comes out really neat, okay? If you have one of the older calculators, you do have to be very careful because the notation doesn't come out as nice. You're going to have to put a lot of extra parentheses, okay? If you have one of the older calculators, I'd suggest that you solve the numerator on your own and then solve each of the magnitudes and then plug it in, okay? The answer here is 165.96 degrees. Whoops, I'm sorry, made a little mistake there. $165.96 degrees. Okay. All right, our next topic is finding whether two vectors are orthogonal. Orthogonal is a big fancy word that literally just means perpendicular. And perpendicular means that the two lines make a 90-degree angle. Okay? So one more time, that fancy word orthogonal just means that the two vectors are perpendicular. So if they're perpendicular, that means the angle between them is 90 degrees. Okay? And the only way that would happen is if the dot product equals 0. Okay? So this is pretty simple. It just says, are the following two vectors orthogonal? Well, you could either do the whole process to check if the angle between the two vectors are 90 degrees, or you can take the shortcut. As long as the numerator is 0 of that formula that we just did, meaning the dot product, then you're good. So if I want to check if the angle, these vectors are orthogonal, that the angle between them is 90 degrees, then I would say u dot v, which means the two numbers in front of the i's, plus multiply the two numbers in front of the j. And you should end up with 12. And then you're going to add a negative 12, which is like saying minus 12, which this equals 0. So check mark, they are orthogonal. Okay. Easy enough? All right, let's move on to projection. Projection of one vector onto another. Okay? So the big thing here that I want you guys to pay attention to is the order of which vector was said first. That is very important for this style of question. Okay? The projection of vector v onto vector w. Okay? We started talking about what it looks like when multiple vectors can have an effect on each other. Here, this is specifically vector v having an effect on vector w. So the projection of vector v onto vector w, the notation will have, if it's v onto w, it'll have the v big and the w small. Okay? So again, if it's v onto w, v is big, w is small, and then these two are the ones that are really going to matter, because v dot w and w dot v, if I switch that order, it'll give me the same thing. But the one that is small is the one that appears in the denominator and over here on the right side of the formula. Okay? So for example, if this said w onto v, my w would be big, my v would be small, and then all of these would flip. This would say w dot v over magnitude of v squared times vector v. Okay? Now, dot product, my numerator, gives me one single number as an answer. Magnitude squared is going to give me one single number as an answer. So this part right here is going to give me a fraction, number over a number. Then you're going to multiply it by the vector that is written here. Okay? So a number times a vector, you're just going to distribute it, and my answer will end up being a vector. We're going to do 2 of these questions. So let's check it out. If vector v is given and w, find the projection of v onto w. If it says v onto w, v is a bigger one, so I'm writing projection of v onto w, which means I'm going to rewrite the formula. V dot w over magnitude of w squared times vector w. Okay? So now the dot product of v and w, I'm going to multiply the two numbers in front of the i's, add them with the numbers in front of the j's being multiplied. That's my numerator. Now moving to my denominator. Magnitude is the square root okay, of w, so I'm going to do of a squared plus b squared. So a squared plus b squared. And then it says to square the answer of that magnitude, okay? Times, I'm going to just write vector w really quick. I'll write that in once I clean this up, okay? So now let's take a look at what happens here. My numerator is going to clean up to a nice, neat answer, okay? In my denominator, a square root and a square are going to cancel each other out, okay? So in my numerator, I end up with -4 plus 24 over a -2 squared is 4 plus 6 squared is 36. And all of that fraction is going to get multiplied to vector w. I'm going to come up here for the rest of our work. So this here is going to clean up to 20 over 40 times vector w right here is -2i plus 6j. Okay, we can reduce 20 over 40 to a half. And then all you're going to do is distribute that 1/2 into the vector, which is going to give you -1i plus 3j. And that is your final answer. And just like we said, we ended up with a vector. Okay? All right, I encourage you to pause and try this one on your own. But if not, let's check it out. If vector v is given and w is given, find the projection of v onto w. So we start off with projection of v onto w. That means I'm doing dot product of v and w over magnitude of w squared times vector w. Okay? So we start off with our dot product, the two i's, 4 and -3 being multiplied, plus the two numbers in front of the j, 3 times 5 being multiplied, over the magnitude of w, which is -3 squared plus 5 squared, all of this squared, times, I'll write vector w in a moment, okay? A reminder, and this will happen in every single question, that this square root and squared will always cancel out, okay? So here I end up with -12 plus 15 over 9 plus 25 times vector w. Let's come up here so we have a little more room. This will clean up to 3 over 34 times vector w, which is -3i plus 5j. And then distribute it in. Remember, like if this was -3 over 1, I'm multiplying fractions, so my leftover answer is -9 over 34i. Plus, if this was 5 over 1, you'd be multiplying the 5 and the 3, so 15 over 34j. And that's your final answer. All right, we have one last thing to cover, and it's probably the easiest thing you have ever seen, and it is called work, okay? If I want to solve for work, here's the notation that the textbook gives you. Here is my layman terms, okay? This, we know that those two lines mean magnitude, okay? So this is talking about the magnitude of the force being done. This portion here represents the distance that it's being done. And then cosine of theta, theta is the angle that's being made. So for example, let's say your car runs out of gas And you have to now push your car to the gas station, okay? You would have force, magnitude, which is the weight of the car. So however much your car weighs would be the magnitude. How far you had to push it. And if I'm pushing it directly straight in front of me, you're going to see that this ends up canceling out because of the angle that's being made. It is 0, okay? And cosine of 0 is 1. So there's going to be times that you see that in a textbook they don't include this. That's because they don't have an angle. But let's say I have something on a dolly that I'm pulling with a rope. That angle that you make with the rope being pulled from the dolly and the floor, that would be the theta you would plug in there. So let's check this out. A person pulls a sled with her dog on it, exerting a force of 50 pounds. Okay, there's your magnitude. On a rope that makes a 30-degree angle with a sled. How much work is being pulled? How much work is being done pulling the sled 100 feet? Okay, so you can imagine there's like a sled here, right? And then someone here has, sorry, I'm not very good artist. They're pulling it. So here is your theta. That's the angle that's being made with the rope and the floor, and then the sled's being pulled, okay? So work would be the force, which is the magnitude, which is 50, times the distance traveled. It was 100 feet, okay, times cosine of 30 degrees. All right, so if you're in my pre-calc class, I'd expect you to be able to do this by hand. Cosine of 30 degrees is radical 3 over 2 times 100 times 50. You have the freedom. Anytime I see a denominator 2, I know I'm going to cut my answer in half. Okay, so you can cut the 100 in half and say 50 times 50. You can cut the 50 in half and call it 25. 25 times 100 might be easier. Okay, so you should have as your final answer, okay? If you are in trig, I would let you put this in your calculator, okay? Now, in your calculator, 50 times 100 times cosine of 30 gives you 4,330.12. And then to double check what we did if we were in pre-cal, that 2,500 radical 3, it would give you the same exact answer, okay? So again, this is an answer I expect more in my pre-cal class here. But for my trig, it's okay if you put 4,330.12.